In a previous video, we discussed finding the domain of a function from its graph. In this video, we're going to discuss finding the domain of a function from its equation. So the thing we need to keep in mind is that the domain is the set of all real number inputs that would give a real number output. So for example, if we have the function y equals x squared minus 5x plus 7, and we start thinking about the domain, it's usually easier to think about the numbers that would be excluded from the domain. In other words, what numbers would not give us a real number output, because there are fewer of those. There are going to be more numbers included in the domain than there are excluded from the domain, usually. So here, if we think about substituting a real number for x, we're going to square it. We're going to multiply it by -5. We're going to add those two results together, then we're going to add 7. Each of those operations is just going to produce a new real number, regardless of what real number we put in for x. So the domain of this function is all real numbers. So in interval notation, we would write that like this. In fact, the domain of any polynomial function is going to be all real numbers, because you're just raising the number to a power, multiplying it by another real number, adding and subtracting. All of those operations will produce another real number. The most common things to watch out for the functions we're dealing with in this chapter are denominators, so fractions, and even roots, like a square root or a fourth root. So for example, if we have the function y equals 3 over x plus 2, almost any number we substitute for x will give us a real number output, because we're going to add 2 to the number, and then we're going to do 3 divided by that result. The only issue we would run into with getting a real number output would be if we were trying to divide by 0. So here that would mean that if x is -2, then we would not get a real number output. Because we're going to try to do 3 divided by 0, and that's not a real number. That's not any number, really. 3 over 0, it's undefined. It's not a number. So any other number, though, any other real number that we substitute for x would give a real number output. So our domain is all real numbers except -2. So let's think about how to write that in interval notation. If we picture the real number line, we're including every single number on that number line except -2. So that -2 breaks up the solution set on the number line. There's a gap between the two parts. So we're going to need a union of two intervals to write this down. So we'll have an interval that represents everything less than -2, and we'll have an interval that represents everything greater than -2. And the union of those two intervals makes up the domain. Similarly, if we have the function y equals x minus 1 over x squared minus 9. Again, the only reason we would not get a real number output would be if we tried to divide by 0. So one thing that sometimes helps is to make sure that we find all of the values that would make the denominator 0, is we can set up an equation where we set the denominator equal to 0. We could have done this in the last example as well. And since this one's a quadratic, we have options. We can add 9 and then use the square root property. Just don't forget the plus or minus. We could factor the left side since it's a difference of squares. Either way, we find two numbers that would make the denominator 0. 3 or -3 would make the denominator 0. So those two numbers cannot be included in the domain. but every other real number besides those two would be included in the domain. So let's draw our number line again. So again, we're shading almost the entire number line. We're just skipping those two numbers. So we're going to have numbers to the left of -3, every number between -3 and 3, and everything to the right of 3. So this time it's going to be a union of 3 intervals. Everything less than -3, everything between -3 and 3, and everything to the right of 3. Note that we're using parentheses and not brackets, because a bracket would include the number, and the whole point here is to exclude those two values. So besides denominators, we also want to look out for even roots, because if the root is even, like a square root, a fourth root, a sixth root, then if a negative number is underneath it, that makes it a non-real number, and we're just interested in real number outputs. So for example, with this function, y equals square root of 2x plus 3, we need to figure out which x values will give a real number output. In other words, which x values will make the number under the radical either positive or 0, because that's the only way that then the square root of that number will be real. So one thing you can do is set up an inequality. We don't want this expression to be negative. We just want it to be either positive or equal to 0. And then if we solve that inequality, that will tell us what x values are included in the domain. So it turns out that the domain, the acceptable values to use for x, are everything greater than or equal to -3/2. So in interval notation, that would look like this. Sometimes we see functions that have both a radical and a fraction, so let's look at some of those. So here we have y equals the square root of 4 over x plus 2. So there are a couple things going on here that we need to take into consideration. We need to make sure that the number under the radical is non-negative. So what's under the radical? Well, it's 4 over x plus 2. So we need to make sure that that fraction isn't equal to a negative number. So it needs to be positive or 0. And we also need to make sure that the denominator of the fraction is not 0. So this becomes an and inequality. So we have to satisfy both of these conditions. Let's look at the second one first. That one's easy. That just means that for the denominator to work, we can't use an x value of -2. So we'll want to make sure of that. And then if we look at this inequality here, and we just kind of think about it, the numerator is always positive. So in order for this fraction to be positive, that would mean that the denominator also has to be positive. Because if the numerator was positive and the denominator was negative, then we would get a negative number, and we don't want that. So this means that the denominator must be positive as well. Positive meaning greater than 0, because again, we don't want the denominator to be equal to 0. So this means that in order to not have a negative under a radical, we need an x value greater than -2. So if you put these two statements together, if we use every number greater than -2, we're not in danger of using negative 2 itself because it's a greater than, not a greater than or equal to. So our domain is just the numbers greater than negative 2. Let's look at another example. So here we have y equals 3x over square root of 5x minus 1. So two things going on here. We've got a radical and we've got a denominator. And this time the radical is over the entire denominator. So if we kind of think about those at the same time, this expression 5x minus 1 is really what we're interested in. So this expression 5x minus 1 could be positive because then we would be able to take the square root and get a real number, and we wouldn't have a 0 in the denominator. However, we don't want 5x minus 1 to be equal to 0 because then the square root of 0 is 0 and we would have a denominator issue. And of course, we don't want 5x minus 1 to be negative because a square root of a negative number is non-real. So the only option here is for 5x minus 1 to be greater than 0. So we can just solve this inequality. And it turns out x must be greater than 1/5. So that would be the domain. Alright, here we have y equals the square root of 3x minus 1 over x minus 4. So again, two things we need here. We need the denominator to not be 0. And we need a non-negative number under the radical. Now this time it's okay if 3x minus 1 is equal to 0 because it's in the numerator. It's okay if the numerator of a fraction is 0. Just don't want the denominator to be 0. Alright, so to satisfy our denominator, we can't use the number 4. And then if we solve the inequality over here, we'll find out what will satisfy that square root in the numerator. So a lot of times it's helpful to graph the solutions. It's an and, so we can only include numbers that satisfy both of those statements. So first of all, the number has to be greater than or equal to 1/3. So we're not going to include anything less than 1/3. But we also can't use the number 4. So we will shade everything to the right of 1/3, except we have to skip over the number 4 because it would make the denominator 0. So our domain then needs to be written as a union of two intervals. All the numbers between 1/3 and 4, including the 1/3, but not including the 4, and then everything greater than 4.